Radio is one of those technologies that feels ordinary because it is everywhere. A car stereo, a phone call, a GPS route, a Wi-Fi signal, a drone controller, a weather radar image, and a satellite link all depend on the same basic idea. Information can travel through space on invisible electromagnetic waves. When people hear the word radio, they often think of music or talk shows. But radio is not just a box with speakers. It is a method of communication, detection, navigation, and control. It lets machines exchange information without a physical wire between them. That single capability changed the shape of the modern world. It made communication mobile, long-distance, fast, and flexible in ways that wired systems alone could never fully achieve. The foundation of radio is the radio wave. Radio waves are electromagnetic waves, meaning they are made from linked electric and magnetic fields moving through space. They belong to the same broad spectrum as visible light, infrared, ultraviolet, X-rays, and microwaves. What separates radio waves from those other forms is their frequency range, which runs from about 3 Hz to 300 GHz. Frequency tells us how many wave cycles pass each second. Low-frequency radio waves have long wavelengths and may travel great distances. Higher frequency waves can carry large amounts of data, but they may be more easily blocked or absorbed. This is why the radio spectrum is not one simple lane. It is a vast set of different regions, each suited to different jobs. A basic radio system begins with a transmitter. The transmitter creates an electrical signal and sends it into an antenna. The antenna is crucial because it turns electrical energy into radio waves that radiate outward. At the other end, a receiving antenna catches a small part of that energy and converts it back into an electrical signal. A radio receiver then processes that signal and recovers the information inside it. This could become sound from a speaker, data on a phone, images on a television, or instructions for a machine. The astonishing part is that the receiver does not need to touch the transmitter. The connection happens through space itself, using waves that can cross rooms, cities, oceans, or orbital distances. A plain radio wave, by itself, is not enough to carry a useful message. To turn it into communication, the transmitter must modify the wave in a controlled way. This process is called modulation. In amplitude modulation, or AM, the strength of the wave is varied to represent information. In frequency modulation, or FM, the frequency is varied instead. Modern digital systems use more complex techniques, changing phase, timing, frequency, or combinations of signal properties to encode streams of data. Modulation is the difference between simply shining an invisible carrier into space and actually writing a message onto it. The carrier wave provides the path. The modulation gives it meaning. Broadcasting is the most familiar example of radio communication. A radio or television station transmits a signal from a tower, and many receivers can tune in at the same time. This one-to-many structure is incredibly efficient. The station does not need a separate connection to every listener. It sends one signal outward, and anyone within range with the right receiver can access it. That made radio broadcasting revolutionary in the 20th century. News, music, speeches, sports, weather warnings, and live events could reach huge audiences almost instantly. Even today, when internet streaming is everywhere, broadcast radio remains valuable because it is simple, wide-reaching, and resilient during emergencies. Radio is also the backbone of two-way communication. A walkie-talkie sends and receives radio signals directly. Aircraft and ships use radio to coordinate movement and safety. Mobile phones constantly exchange radio signals with nearby cell towers, which connect into a wider communications network. Wi-Fi uses radio waves over shorter distances to connect laptops, phones, cameras, and smart devices to the Internet. In these systems, the challenge is not just sending a signal. Many devices may be trying to communicate in the same area, so networks need rules that manage timing, frequencies, channels, authentication, and error correction. The basic idea remains radio, but modern systems build sophisticated coordination on top of it. Radar shows that radio can do more than carry messages. A radar system transmits radio waves toward an area and listens for reflections. When those waves hit an object, part of the energy bounces back. By measuring the time it takes for the echo to return, radar can estimate distance. By measuring direction and changes in the reflected signal, it can help determine location, speed, and movement. This allows radar to detect aircraft, ships, spacecraft, missiles, storms, and terrain even when human vision is useless. Darkness, foggy clouds, and distance do not stop radar in the same way they stop ordinary sight. Radio becomes a way of sensing the world. Radio navigation uses signals as invisible reference points. GPS is the best-known example. Satellites broadcast precisely timed radio signals from known positions in orbit. A GPS receiver listens to signals from several satellites and compares their timing. Because radio waves travel at a known speed, tiny timing differences reveal how far the receiver is from each satellite. With enough measurements, the device calculates its position on Earth. The receiver does not need to see a road, landmark, or map printed on paper. It calculates location from radio timing. Other navigation systems, such as aviation beacons, use related principles. Radio allows position to be measured through signals rather than visible markers. Remote control is another everyday use of radio. A garage door opener sends a short coded signal that tells a motor to open or close. A car key fob uses radio to lock, unlock, or start a vehicle. Drone controllers send continuous commands through radio links, telling aircraft how to move. These applications may look simple, but they require reliability and security. The receiver must distinguish the correct signal from background noise, interference, and unauthorized attempts. Modern systems often use coded signals, rolling codes, or encrypted communication to reduce the risk of copying or spoofing. Radio makes control possible at a distance, but distance also makes trust and signal design important. The story of radio began as scientific discovery before it became global infrastructure. On November 11, 1886, German physicist Heinrich Hertz proved the existence of radio waves. His experiments showed that electromagnetic waves could be generated, transmitted, and detected, confirming theoretical ideas about electromagnetism. In the mid-1890s, Guglielmo Marconi built practical equipment for long-distance wireless communication. In 1895, he sent a wireless Morse code message over more than a kilometer. On December 12, 1901, he received a transatlantic signal. These achievements mattered because they moved radio from laboratory demonstration to practical communication. They showed that invisible waves could carry real messages across serious distances. Radio broadcasting soon turned wireless communication into a mass medium. On November 2, 1920, Westinghouse Electric and Manufacturing Company in Pittsburgh broadcast live returns from the United States presidential election under the call sign KDKA. This was a major step toward commercial radio as people came to know it. Instead of receiving information through newspapers after a delay, listeners could experience events as they unfolded. Radio created shared moments across large audiences. It also changed politics, advertising, entertainment, education, and emergency communication. A voice in one studio could reach homes far away, creating a new kind of public space built not from buildings or wires, but from signals. Because radio waves share the same physical spectrum, radio cannot be left completely unorganized. If too many transmitters use the same frequency in the same place, their signals interfere. If transmitters use excessive power, they can drown out weaker services. This is why radio emissions are regulated by law, and why international coordination matters. The International Telecommunication Union helps allocate frequency bands for different uses, including broadcasting, aviation, maritime communication, satellites, navigation, cellular networks, science, emergency services, and defense. This invisible structure keeps the wireless world from collapsing into noise. Radio may feel effortless from the user's side, but behind every clear signal is engineering, coordination, and rules that make shared wireless space usable. If you found this helpful, please like this video and subscribe for more explainers.